Log on, tune in, find out. Another good idea from Cambridge.
Collect very good people regarding spatial statistics. It's hard to find a better person who represents spatial things, you can see.
It's not a good compliment.
I appreciate very much what Werner Müller from the University of Linz contributed to experimental design. In my personal opinion, he opened up new opportunities for experimental design. What I presented this morning was my aim to include partial differential equations in practical applications, but I think that what Werner uses is even closer to applications, as you can see. So, Werner Müller.
Thank you very much for the nice introduction. It's fine back there?
It's fine in this room.
Yeah, okay. And I'll use it.
I think you need to use it for the recording.
For the recording.
Red light.
Okay. Thank you very much.
Thanks first of all for the invitation, and it's a great pleasure to be here in Cambridge, and it's a wonderful opportunity to tell you a little bit about things that we've been doing in the past years. That's not me alone, but the whole group of collaborators I've been working with, and the list of collaborators I would like to thank is here. This is Roger Bivand, Daniela Gumprecht, Luc Bronsato, Juan Rodriguez Diaz, Markus Reda, Maria Rivas Lopez, Milan Stelig, and Helmut Weidel. So, and we will refer to parts of their work at different places of the presentation. I'm going to talk a little bit general, give you an introduction. You will notice that at our department, the structure is a little bit similar to Rainer's department, where the younger people have to do the more complicated problems. You will see after the coffee break that it's the same. We have the same rule in our department. This gives me a good reason to show you some more. Yeah. Let's begin with the outline. And Dariusz already told you that space is the final frontier. Yes, this is the final challenge that we have, and I will talk a little bit about that and why I think it is so, and things that are connected with it. I will say something about different types of spatial models that we can look at. I will say something about designs for detecting spatial dependence. I will give an applied example one. Then I will give designs for spatial prediction and estimation. That was already mentioned also by Radoslav in his talk, that there is we have two objectives that compete. And then and this part might be familiar to some of you who have heard me talk before at different occasions. But this last part, does it all connect somehow? We've just looked at this very recently, so this will be the new part. So those of you who know all that, they can sleep through the next 40 minutes or so, and then I'll wake them up. And good. Okay. So I have some introductory slides that I could skip probably because they are, but nevertheless, let's say a few words. What is spatial data? Well, spatial data has the characteristic that attached to every observation, you have a set of coordinates that identifies the position, perhaps geographical position, of the respective data collection site. That's clear. And what is very, very obvious to us, but is not very obvious, I think, to many of the people applying or the applied people working with spatial data, is that the set of locations of the data collection sites, what we call the design, decisively influences the quality of the results of the statistical analysis. This is effect which is quite obvious for us, but it's not at all obvious when you talk to people working with these kind of data. And this is a point you have to persuade them that it's really the case. Now, what are there are mainly two approaches to data acquisition in this field of spatial data. One which is in the literature rather confusingly called design-based approach. I'd rather call it probability-based approach, and it's basically a model-free methodology which is oriented towards restoring unobserved data points, or maybe estimating principal notions like grand means and things like that. Yes, and this is coped with usually methods from sampling that stem from sampling theory. And there's a rather good overview book which is called Sampling for Natural Resource Monitoring by Bruce, De Gruyter, Notters, and fourth author I forgot, but I mean, really good book about this. And the second big area, which is a little bit more familiar probably to us and to the audience, is the model-based approach, where the aim is to estimate the structure of the data generating process or some parameters of some assumed models or functions of these parameters and do predictions out of this. Yes, and this is of course the data collecting question here is of course based in what we all know, optimum experimental design theory. This is closely connected here, and well, this is I give you this is my small contribution to this field is this book called Collecting Spatial Data, and really it's these two areas. When you look at publications, they either refer to this or this, and sometimes they make connections, but mainly this is a little bit separate things. Since we're in this community and I'm more familiar with this, we are going to talk about this exclusively now. Now, when we are here, we can still we do design, and then we have to do some estimation stage, or we have to do something with the model and the parameters, and then we still have, in some sense, two modeling paradigms that are around in the literature, and they are also quite confusingly named, but they come under different notions. But one of them is called now, and now this name is more and more used, Gaussian Markov random fields, and how they're characterized. They are discretely indexed. That means that we have observations on a discrete grid, this discrete lattice. Usually, we observe some aggregate observations on some lattices, or like some areas where we have some means over the areas, or some total counts or something like that. And this formed an area that is mainly known as spatial econometrics, and it came also, most of the theory came from the econometric side, and it came from analogous developments from time series econometrics. So this is the root of this piece and part of modeling paradigm. And the second modeling paradigm rather comes from originally geological sciences and runs under the name of geostatistics. And predominant model class are Gaussian fields. The Gaussian fields are continuously indexed, yes, and we observe spatially varying processes. And I have here two prominent books. This is the book by Luc Enslin, Spatial Econometrics, Methods and Moments, and this is the book Geostatistics by Gilles and Delphinet. The question is, yeah, the question that I'm going to address in this talk is, let us discuss design problems that arise here. Let us discuss some design problems that arise here, and then eventually, is there some connection, and can we connect these things? Okay, let's start with this part, spatial econometrics, discretely indexed stuff. So how do the models usually look like? Well, they're spatial regression models. Here, one of the typical ones of those is the so-called spatial or simultaneously autoregressive model. And you have some spatial dependence in the error term. So you have a sort of a standard regression model with some covariates. And then you have, in the error term, you have some autocovariance. And the autocovariance is characterized by two things. One is this famous or infamous matrix W. W is the so-called spatial weight on neighboring matrix. And it characterizes whether there is any connection between any of these discretely indexed regions or points in space to a neighboring point. So the simplest type of weighting matrix is a matrix that just consists of zeros and ones. It has a one there when the corresponding element is a neighbor in some predefined sense of the other element. Yes, so rows and columns define whether the column element is a neighbor of the row element or not. Yes, so it will give a 1 or a 0. You can have more complicated structures like weighted neighborhood, weighted by distances and things like that, but really not relevant at that point. And then, of course, rho here is the autocorrelation parameter. So the size of rho governs the strength of the neighboring autocorrelation that is in the system. And you can reformulate that, and then you can do all kinds of things. And you can have different versions of these parametrizations. Actually, all that is essential for us is how these specifications differ in the variance covariance matrix of the errors. And they, of course, depend upon the spatial process. So for this spatial autoregressive error model, this covariance matrix omega, which is, of course, a function of rho, looks like this. Yes. And then we have this special class of models which are called conditionally autoregressive models, which are slightly characterized differently because they have a Markov property, so the dependence is always on the nearest neighbors, and this is they are in accordance with what I told you before, what is called the Gaussian Markov random fields, and they have, for instance, a covariance structure which is looks like this, slightly simpler. But for us, it's just interesting to know how this omega looks like. We will just use sort of the structure of the omega and of the W, of course. But otherwise, we don't really care. So what we started up when we looked at these problems, we started up with the SAR process because it was the more strongly used one in the spatial econometrics literature. More and more these processes, these CAR processes, take over, especially because they have these Markov properties which makes them easy to estimate. They make sparse covariance matrices, and so they have all kinds of nice properties. And there's a really nice book about Gaussian Markov random fields by Howard Rue and Leonhard Held, which just arrived a few years ago. So let us continue with first this SAR model, and I give you the example. The example is example from Brazil. The Cerrado. The Cerrado is this area in Brazil, which is sort of pre or attached to the rainforest. So it's some special habitat for all kinds of animals. And the example is taken from the paper Autoaggressive Modeling of Species Richness in Brazilian Cerrado by Vieira, Blamieres, Diniz, Filho, Bini, and Rangel from the Brazilian Journal of Biology. And what they wanted to do is they wanted to investigate whether there is any spatial autocorrelation in the biodiversity by counts of numbers of species at various points in the Cerrado. And they have discretized this, so there's a discrete grid. We have, they were so nice to also send me the data for that. And what they did is in every of these areas here, of these squares, sometimes they are not squares, but these areas, they just went there and counted the number of animals that they encountered of various types, mammals and reptiles. And so this is a count of animals. So the example 1, the response that we are modeling is count of numbers of species in mammals, birds, and reptiles. And we'll just for the example, just use one of these. And what is characterizing this too is that we really don't have much prior knowledge about the type of models that would describe species richness. Yes. So and of course if we don't know models, we don't know anything about parameters as well. So all that really is to do, and what was done by them in their study, is to detect and then quantify the spatial dependence. Because of course, if they would be in the lucky case that there is no spatial dependence, then they could just use standard regression techniques and be in a very advantageous position for their inference, which they have to test before proceeding. So, what is spatial dependence? It's also you don't need this, but for some audiences I have it here. I mean, the main, what they call the first law of geography by Tobler is, it says all things are related, but nearby things are more related than distant things. Yeah, this would of course but then only describe positive spatial dependence, which is the standard case in these kind of data. And then, this is perhaps a more formal description. Spatial dependence is the extent to which the value of an attribute in one location depends on the values of attributes in nearby locations. And there is one guy who has very strong feelings about spatial dependence. So hell is a place for that. Okay. Now, how do we measure this kind of dependence? There are several measures around. One of the very classical measures, which is almost standardly used, is the so-called Moran's eye. Moran's eye is due to Patrick Moran, and he suggested in 1950 that one had to look at some aggregate weighted, it's clear, some kind of covariance type measure that is suitably normalized, and the weights, of course, would correspond to these neighboring relations, so that they would be the entries of the W matrix. Yes, so you would give 1 here for neighbors, 0 for non-neighbors, and it's clear that this is a rather good indicator for whether there is a positive autocorrelation or positive dependence in the spatial data you have. This was generalized for regression residuals. It's actually the case we need here. We most probably always have some cofactors. Not really so much in this example, as you will see later. But this was generalized by Cliff and Ord in 1981 for regression residuals, and then it looks like that. And we have here we have this M, this is the projection, standard projection. We have this W again here. It's clear that it can be written in this quadratic form format, a ratio of quadratic forms. We will use that later. So what is it good for? It really established some kind of spatial relation, that you don't have a natural ordering of spatial objects, yes, but the ordering of spatial objects is in some sense artificially created by this W, because when you plot the variable, the measurements y that you have, the observations against their spatial legs, so the w y's, then you get something like this scatter plot, sometimes called Morin scatter plot, which describes the strength of the spatial relation in your data. When you then draw the regression line through it, then it's so that the slope of the regression line corresponds to Morin's I, which is also a nice property. So it has some really appealing, most statistical meaning to it. Of course, there are other of these measures, but we will discuss some of them later. But now then we want to proceed in doing some inference. We of course need to test. We have a sample results. We need to test whether the a certain observed Morin's I is significantly different from 0 or not. Yes. So what you do is usually is that you use a normal approximation and you use a standardized z-value and then test against normal. This goes back to Henshaw, 1966. So the expectation is just that the trace of this k, where k is the half m w divided by n minus k. K is here the numbers of parameters in the regression, and the variance looks like that, a little bit more complicated, but involving only k again, and the numbers of observations, of course. So this is a really usually quite reliable normal approximation that gives you the distribution under the null. Of course, when you do statistical testing, what you also want to know, or frequently should want to know, is the power, and we will need that. So we also need the distribution of Morin's I under some given alternative. So what we did is we looked at the model they had in their example, the Serrato example. They had an even simpler model that I showed you. They didn't have any cofactors. They just had an intercept beta, and they just had a spatial simultaneous autoregressive error model. And under this alternative here, we can find slightly more complicated formula for the expectation and the variance, and then we can again use normal approximation. So this holds in most of the cases rather well. It's a little bit involved. We have some numerical evaluations of integrals and things like that, but there is code around, so we didn't have to code that. It's just you could take it. There are programs that already do that for you. So it's not as difficult as it seems. When we did that, we noticed that the normal approximation holds rather well in many cases, but there are cases where it could be really bad. So we looked at whether we have alternatives for that, and there really is also, well, they call it the exact distribution, but it's of course another, maybe more exact approximation than the normal approximation, and it is due to Diffelsdorf and Boots and Kepler, seemingly independently, who use this structure of the Morin's I as being a ratio of quadratic forms, and they came up with an exact distribution based on Imhoff's formula. Yes, much of this can be found in a very nice, very small book by Michael Diffelsdorf, which is called Modeling Spatial Processes, Springer Verlag. And we could use this distribution instead of the normal approximation, and you can proceed as if you were doing the normal thing. Okay, let's go a little, make a little detour on other. There is, of course, the very famous other indicators of spatial dependence. There's the famous gated statistics. The other statistic that came up recently is called Apple. It was proposed by Lee, Calder, and Cressy in 2007. It looks like this. You see, it's a little bit of a different version of the Moran's eye, and it aims at some better reflection of this SAR parameter rho. We tried to use that too. Of course, we had to find distributional properties of this thing, so we had to derive the exact distribution of this, and this was done by one of my students jointly with me, and appeared in the celebration volume of Andrei Pazman's 70th birthday. And we have some comparative simulations in there, and implementation in R code and discussion. A little bit different also, we can look at local Moran's eyes. If we don't, the Moran eye is a global measure, but you can have localized variance at every spot when you don't use all the data. And we have done something on local Moran's eye tests also, with some implementations. All we have is really now integrated into this R package, SPDEP, spatial dependence, which is run by Roger Bivand, and which can be downloaded, of course. And yes, so we're here, and now we're really ready to go into the design issue. We haven't talked about designing now. Okay, so what would be, and we go back to the Moran's eye because it's the easiest case. So what would be a good way to design for detecting spatial dependence based on the Moran's eye? It's rather simple, of course. The purpose is we would want to have a design that in some sense maximizes the power of the Moran's eye test. Okay, so what we'll do is we minimize this probability here, and then we can reformulate this, and we know that we have under the normal approximation, and if you don't use the normal, you just replace the normal by the exact distribution. We look at the argmin of the standard normal, and with these arguments here, and you see that what you have in there, you have the variance under the null, you have the expectation under the null. They are quite simple. The expectation under the alternative, and the variance under the alternative. All of them contain only the W's as the element. So when the W is fixed, and of course as an argument, they have the locations xi. This was done in one part of the dissertation of Daniela Gumprecht, and was done jointly with Juan Rodriguez Diaz. The disadvantage of this, of course, is we are not at all in the realm of what we know classical optimal design theory, because this is a highly non-convex thing that we're optimizing here. So we really need to use different optimization techniques. Either we do enumeration in small examples, full enumerations, or then we do some simulated annealing and things like that. So this is the design question. Now let's go to one of the simple examples, because I don't want to directly go to the real example. We have in this paper several simple examples, like on regular grids and with a few numbers of observations. But we wanted to find an example where we could investigate whether the use of the normal approximation or the exact distribution of Moran's eye would make any difference. And so we had to find an example where it was known that by this constellation the difference would be potentially high. And this was designed, it's called the BO7 structure, and it's you can see it here. So those are eight potential observations which are connected in this graph here, and they were designed in order to make the normal approximation fail. Yes, And you can find them in Tiefelsdorf's book, for instance, where he does simulations and shows impressively that the normal approximation really does very badly in this setup, and he has another one too. But now we can do an optimal design on this, yes, we can select which of the points we should observe twice or thrice, and we can find for different, of course, depending upon the level of autocorrelation that we assume, yes, we can have efficiency improvements of 17 or 165%, depending upon a strength of assumed autocorrelation. But what is much more remarkable, I think, than any of these things, we have seen all this before in design talks. There's always improvement, you know, there's always, this is not so much impressive for me. This is much more impressive. And I don't have an explanation for that. I think almost all of our examples, or even the less complicated ones, the real ones, everything that we calculated, that we found almost no difference between using the exact distribution and the normal approximation at the optimal design. So when we have an optimal design, so the optimal design sort of acts like a regulator, yeah, to make the normal approximation work well for some magic reasons that I cannot explain. Yes, but it's some kind of side issue that we found, some side effect that there is no real good explanation for that we have for that. So here I wanted to show you a movie, but I don't really want. I didn't want to risk it fail. Where you see where from the original grid, by exchange and elimination, we arrive eventually at this setup, which constitutes, in our mind, of course, the optimal design. Of course, when you do a different kinds of algorithms, you will end up at different places, but they will be all qualitatively similar, so the improvements are similar. So you see the optimal design here is rather sparse. Yeah, it doesn't contain all the grid points, yes, and all the and doesn't contain many connections. So it will give you a very nice matrix to work with. So this is also an advantage and an improvement. So let me first conclude here. So we have the situation that we can have very severe approximation errors. This was found in Poots and Tiefelsdorf, but not at the optimal designs. So this is, I think, was most remarkable about this part. Optimal designs can be rather sparse, and then we should do regular power analysis, of course, by using SPDEP. Okay, this was the first bit, discretely indexed spatial data. What about the other thing? Example 2. Example 2 is a little less exotic than example 1. This is the Südliche Tullnerfeld. The Südliche Tullnerfeld is a place very close to where I live and work. I live approximately here on this map, I would say, here. I work approximately here, and the corner doesn't, but not very far out of that corner. And it's along the Danube River. And it's used by, you know, hydrologists very much because it has a very homogeneous aquifer. And so it's used like a test bed for all kinds of things that hydrologists want to know. I've used it before in an article in Envirometrics. And how does it differ from example 1? Well, the response here are various groundwater pollutants: kalium, nitride, chloride, nitrate, atrazine, and others. We have much more knowledge, prior knowledge here. We have data from an existing monitoring network available. So gives us good prior estimates and everything. We have a model class then that can be assumed to be known because the hydrologists have good idea about how these models look like. So our aim now is estimation of parameters, or functions of parameters. Yeah. Like maximal concentrations. That's what hydrologists are very concerned about. Okay, and of course, we are continuously indexed. We can measure at any spot we want to put within this area. We want to put our measurement station. So what is the setup? You know that well. For these continuously indexed fields, the data is observed at coordinates z. They are from this R2, and they're being generated from by random field. Random field could be anyway, but it's parameterized by trend parameter beta. And then we have typically we have a parameterized covariance function for the errors z, which is parameterized by some other parameter thetas. Okay, and really the sort of the Bible for these kind of models is the well-known book Statistics for Spatial Data by Noel Cressy, and you find a lot of material about this in there. Okay, so what is the problem here? Here we have now this thing about the two purposes that Radoslav told us. We can really do two things. We can either do prediction. We want to predict the field at unobserved, unsampled locations, or we want to estimate because we want to learn about the process that we have here and modeled, that we have modeled. And what is the typical way of going about this? That is to use the universal Kriging method of universal Kriging. And in Kriging, what you do is you assume the covariance structure as known, which is, first of all, it sounds a little bit strange, but you assume it known, then you know that the Kriging estimator is gives you the best linear unbiased predictor, and then you can use for estimation the corresponding GLS estimator. What is done in practice really is, since it's not, the covariance structure is not known, you have a first stage which is usually called variography, so where you sort of pre-estimate from the same data the covariance structure and then plug it in here. Then you have this feasible GLS estimator and then do Kriging from this pre-estimated version. Alternative, you can do a full maximum likelihood or a restricted maximum likelihood of the full parameter set and insert for prediction above. This has an important effect on all kinds of things, especially in our design purpose, as you will see soon. The fact that we use sort of the same data set twice. Okay? Because how is uncertainty usually in Kriging assessed? Many of you know this is the famous Kriging variance. You look at the Kriging variance. The Kriging variance has a simple expression. I don't give it here, but I just give it in this way. This is the Kriging variance that's usually used. And how is then design done? Okay, frequently it's done. You look at the design, which minimizes the maximum Kriging variance over the region. Okay, this is sort of one of the standard approaches for spatial design. Of course, the mistake you're making here is that you do not account for the fact that you have additional uncertainty that comes from the stage of estimating the variance covariance parameters from the same data set, and you have to introduce this additional uncertainty to make sure that you capture the full uncertainty that you have. And there have been approximations to this Kriging variance to the full Kriging variance, I would say, go back to Havil and Jeske and a variant by Abt in 1999, and those approximations were used and supplemented to the Kriging variance, and you can see them here. This part of the expression by Su in his dissertation and by Zimmermann in a paper, seemingly independent too, as the new design criterion. I'd call it the corrected Kriging variance or whatever. Zimmerman calls it empirical Kriging criterion, but it's just a sort of a corrected. So it's the same style as you look for the minimum of the maximum corrected Kriging variance, and the correction includes this capital M theta here, which I didn't tell you about. This is the information matrix for the parameters, for the covariance parameters. So you can see that this criterion really is computationally extremely demanding, because you have to here you have to minimize over the design, which is potentially has many sites. So it's combinatorial problem up here, and then you have embedded this maximization over all practically all the whole candidate set, which is potentially continuous. So this is really an extremely demanding problem, and you can rarely do it in the way it's written here. So we have to find alternatives here. Well, they did it. They did in their papers. They used some simulated annealing, and they did some simple examples. But it's really going to the limit. So let's talk about space fillingness a bit. Yes, space fillingness. Why is it so interesting in this context? We have a similar, or almost exactly the same setup in what is called computer simulation experiments, although in higher dimensions. This was set up by the seminal paper by Sachs, Welsh, Mitchell, and Wynne, and some time ago. And the predominant strategy, and you can read all this up in this very nice book by Tom Sentner and Williams and Knott. The predominant design strategy in computer simulation experiments is use space-filling designs. Maximum Latin hypercube things, space fillingness. I was at a conference a couple of years ago in Saint-Etienne where the computer simulation guys, and they were all talking about how to make their designs more space-filling. Yes, I can make it more space-filling, and I have even a more space-filling Latin hypercube than you. And I felt a little bit out of place, because I wanted to tell them that space-filling is not always a very good idea. So well, thanks for David Steinberg, who saved me a little bit of being stoned there. So let me give you an example, very, very simple example. A bivariate Ornstein-Uhlenbeck process. So we have a constant trend in two dimensions, and we have the covariance function, which is sigma squared, and then it's e to the distance between the locations, and the parameter, the covariance parameter, the guiding parameter is theta. So we can look at a 7-point maximum design. This is here, and here, and here, and here. And then we can plot the isolines of the EK criterion. Okay? And you can see the EK criterion, it has values between here, I don't know, 2 and 2.8 or something. And the maximum of the EK values is 2.68, which is achieved at these 2 points. Okay? So this is for a space filling design. Now let's look, what if we optimize here? What if we optimize for finding the best EK value? Well, the result is this. So this is the optimal design. It's very, very far from space filling, as you can see. Yeah, the EK value is 1.18. So this is corrected prediction variance, so it's much, much lower. You see, I mean, this is not space filling at all. So the natural question, and the maximum point is here in the corner. So the natural question is there a relationship between non-space fillingness and a sort of EK optimality? Okay, and what we did is we just randomly sampled thousands of to get an impression. Randomly sampled 1,000 7-point designs, and then plotted the criteria against each other. You see, it looks like that. Here we have on a horizontal line, we have the minimal distances, and here we have the EK values. So EK values are supposed to be low, distances are supposed to be high. Yes, those are the optimal values, the dotted lines, the dashed lines. Yes, so you see it's really a vice versa relationship between space fillingness and EK optimality, which is kind of disturbing because this means really that space filling is not entirely good thing to achieve. Okay, now let's go to the problem of optimal design and how can we use optimal design efficiently here. Well, you know all this. We've seen this slide many times, but I will draw your attention to what we can learn from Kiefer-Wolfowitz theorem. One part of Kiefer-Wolfowitz theorem is that it established a relationship between a criterion which is prediction-based, which is the G criterion, and it's, you see, it almost looks like the criterion we had before, just except, of course, this is in uncorrelated error case, except we have a different variance here. Yes, we have we can just plug in here this corrected Kriging variance to have an accordance, and it established connection between this prediction criterion and this estimation criterion. If we can do this too in the correlated case, this would be really fine, because these criteria are, of course, much easier to evaluate and to optimize. Now the naive question, or the idea is, well, what kind of determinant could we use? What kind of information matrix could we use here? Well, the full information matrix for estimating the trend and the covariance parameters looks like that. It contains two blocks. One block is related to the trend parameters, this is standard form. The second block is related to the covariance parameters and looks like this. Okay. The problem is they don't have, a scaling that relates them in a natural way to each other. So how can we combine this in a reasonable way? First of all, of course, we have three cases. We are interested either in beta only, or in theta only, or in both. Okay. Case one, case two. So the idea, of course, is to use the natural idea of compound designs. Compound designs, you have two different criteria and different information matrices, and you combine them by using the convex combination with some parameter alpha that you choose, like tuning parameter. And you can, what we suggest in a paper by Milan and me was just to use for this purpose some kind of criterion like this. Yeah? So when you log it, it's a compound criterion, and you have this alpha as a weighting. So you give some weight to the trend part, and then you give some weight to the covariance part. Only you don't know how much weight to give, which is the open question still. But you'll see. Okay, let's go to an even simpler example where we have results, theoretical results. The one-dimensional Ornstein-Uhlenbeck. Yes. For the case one, we know when we only look for trend parameters, we know from Kisilak-Stelik, Detekun, and Pepelishev, and also from Radoslav, that the uniform design is the space-filling design is optimal, is the optimal. We know in the case two, where we don't look at the trend, that the d-optimal design collapses into one point. Yes, and we know from our experiments and experiences that the case three is sort of a regulatory version between these two things. So we have a not uniform, not collapsing design here. Okay. Maybe I'm going to skip this small example with 3 points because I don't have enough time. But the conjecture that we made is that we can always find an alpha such that compound designs are then close to these AK optimal designs. Of course, we could immediately find an example where a strict relationship could be disproved. So this was done by Helmut and me in a paper. But we again made an experiment as we did before. Like we plotted 1,000 random designs or 2,000 random designs and looked whether there is any accordance between these criteria. And this looked like that. And it doesn't look so bad, yes? So here we have this for two values of alpha, 0.7, 0.8. You have, this is what we call CD optimality, is a compound D optimality here on this axis. and AK optimality here. So you can see there's relatively good accordance. We can find these. We can also, the efficiencies are quite good, yeah, of the respective designs. These are the optimum points. There is some strange bifurcation when the alpha goes up. And of course, the whole thing breaks down when the alpha goes up even more. So a big alpha and a very low alpha, they don't work. So you have to find some reasonably, still now we can only find it by experimentation, but we have to find ways to make this more clear to us. But it looks rather well. And how do the CD optimal designs for these two cases look like? Again, very different, and very different from space filling, yes. So for alpha 0.7, you have 2 points here, 2 points here, 2 points here, 1 point here. And for alpha 0.8, you have 1 point, 2 point. So very different, definitely not space filling. Yeah. Okay, then I had, this was the slide in case I would, I would have too much time to fill. I would talk about several issues that you have that we have neglected, but I'm going to skip this now. You can read that up. I'm going back to the example that we had, water quality monitoring network. To make computations easier again, now I approximated the continuous region by a grid, and we used some hybrid exchange algorithm. We had to postulate, of course, our covariance function. We used the spherical covariance function here. And this is the case one, which is not interesting at all, of course. For a linear trend, the expected happens. All the points go to the boundaries of the region. So it's not exciting. But, of course, exciting or interesting is the case three. Case three really results in a 7-fold improvement in the criterion over the existing network. This is the result after the optimization. Now this is not a real good comparison. What does it mean, 7-fold? The criterion, it doesn't give you an idea. So what you could do, of course, is to compare the other way around and say, okay, how many points, how many observation points can I eliminate optimally so that we still have the same information as in the original network, okay, out of these points. And this is a more reasonable comparison. We can achieve an equivalent network with 21 sites. So it's there were 36, and so it's 15 sites less, equivalent amount of information. So it's quite an impressive gain here. Good. Now I come to this new and last part. This is a relatively fresh paper read before the Royal Statistical Society recently, one of the last sessions, by Finn Lindgren, Howard Rue, and Johan Lindström. And what they provide in this paper is some explicit way of linking Gaussian fields and Gaussian Markov random fields for a certain class of covariance functions, so-called Matern covariance functions. But Matern, a rather rich family, so it's not very restrictive here. For any kind of a grid, this is the important thing, because previously these linkages were only known for specific grids. But now the grid is arbitrary, which is, of course, the interesting thing for real application. And we were in the lucky position that we could contribute to the discussion of this paper. The natural thing for us to ask was, now we have a link between those two things. Can we also link the respective designs that we found for either the cases? Yes. Are there any linkages? There should be linkages. If there's a real link, there should be also a link in the designs. Again, we took the example 3. They provided all the code, fortunately, and all the so we got the R script, and so we could just run the R script and plug it into our things. So we didn't have to do really much. So the example 3 they have, the example 3 here, the example they have in the paper is leukemia survival in Northwest England. It's taken from a JASA paper from 2002. And you see here there are several districts, I don't know, 24 or something, and they all have these counts of leukemia survival cases here. And of course, there is no design question here posed, but we imposed one. Yeah, we said, okay, assume you have some budget constraints and you're only allowed to count in 3 out of these 24 districts for whatever reason. Of course, we chose that because we could enumerate all the possibilities. 24 out of 3 is 2,000 something. Yes, so it was an easy task. So we can enumerate everything and really plot all these values against each other. And so example 3, the response accounts of survivals. Here we have prior knowledge. Fortunately, we have some given error covariance function, variance covariance matrix, which was given from their example. So the omega was known. We just had to plug in our omega. It was a car model, of course. And they also provided an estimate of rho of 0.24, which we needed because, of course, I didn't talk about this, but everything's nonlinear, so we need local. We do local linearization, of course. Yes. And now the aim is to detect and quantify relationships between these design criteria. Okay, let's look at that scatter plot of all these 2,096 designs. It looks reasonably well, and I have plotted here the Moran's eye power of the Moran's eye, and the EK. So you can see, this is really in accordance. Unfortunately, the accordance is not quite good there where it really matters. Yes, it's here. Yeah. This is a slight problem, but we found by changing the problem slightly that it really all depends upon the powers. This accordance is very good for very low, when the powers are very low, when you have few observations. Yes, the more observations you have, the higher the powers is, the less is the accordance of these criteria. And then, of course, you cannot use this criterion for this one and in exchange and have any. If you could do this, you could, of course, have a lot of computational gains because these Gaussian Markov random fields, they're much easier to compute. So you really need a setup where this works. It works very well when the nuggets are strong. Okay, so we doubled the nugget and then we really extended into this area. So this is for strongly correlated with high nugget, it works well. And then here the other panel is now for the CD criterion. Of course, you want to have a high power and high CD. So this also looks very good. So this probably really could help, especially in the cases where it matters, to replace one of the criteria against the other. Yes, but it needs, of course, much more systematic thinking about it and much more systematic work about it. Okay, let me make 3 advertisements on 3 slides, and I'll be right in time. One, of course, I made already, shameless as I am, 3rd edition of my book, 2007. Next one is, you might know about this journal, Statistical Papers. Not very well known, but reasonably well known. I just want to point out that it has new editors, so please submit good papers to Statistical Papers. Okay, nice impact factor now. Okay, and then the third thing is ISBIS. ISBIS is I'm now made responsible for the membership of ISBIS. Yes, and ISBIS is a section of the ISI, one of the many sections. So if you're not section member of any ISI section and you want to become ISI section member, and if you're ISI member and not member of a section, you can be for free section member, then please join ISBIS. Thank you.
Thank you very much. Now it's time for questions. Please.
In your presentation, you contrasted these designs with, let's say, random designs, scattering over fields. But how do you feel if a design is not random but quasi-random, which is much more uniformly distributed. I mean, quasi-random is deterministic design, which also fills, let's say, space. Is it a large difference in your opinion or not?
Well, I wouldn't use any of these random designs as a design. I just use the collection of 1,000 random designs to show whether there is any connection among all possible designs. Yes, it's probably more useful to use this kind of designs if you really want to use a regular design. You wouldn't use a random design. No, of course.
Other questions? The overview was very nice, but as for me, one thing is interesting. What is the state of the art when you want to introduce the factor of time?
Yeah. Factor of time is good question. Of course, one naive way to do it is just another dimension, because it restricts the type of covariance functions that you can use, because of course in time you have some different behavior than in space.
Exactly.
Yes, but there is some progress in that. Of course, there's not much done in dynamic design in time. Yeah, where really there is movement in time, which is the most interesting link to what you're doing. Yeah, that's really something that is sort of open problem, open for research.
Are there any questions? Henry?
Do you have a general kind of sentence we can take home, which is like if you're estimating covariance or correlation length or something like that, you need a lot of clusters with points close together.
Yes.
But if you're estimating broad fixed effect models or the first few components of a column wave expansion, they tend to spread out.
Yes.
Do you have a sentence? Is that the right?
That's the sentence. Thank you.
Okay. Thank you very much, Werner. Once again.